Yeah, we're going to do a wavelength. So, okay. So, with the opera singer hitting a specific note causing a window to break, that's the same thing that happened with Bill Nye and that bridge. I guess Bill Nye didn't break the bridge. In the Bill Nye video, there was a bridge that broke. Or when I showed the video right after that with the little kid that broke a glass, both of those things are resonance. The bridge got its natural resonant frequency, the glass got its natural resonant frequency. Apparently, opera singer hit that specific note. There was that window's natural resonant frequency, and the window started being like, and it broke because it's made of glass. And it can't bend like that real good. Anyway, that's resonance. Okay, now hopefully when I switch screens this time, the video won't turn off for no reason. So, let me make sure that it's going to be okay.
Wait, sir.
What?
Does everything have a resonance?
Vibrate at like a high enough
Yeah, I suppose
frequency
so. It
to
depends on its shape.
So like,
Depending on its shape, it's a specific wavelength that sets up a standing wave, and it's it'll.
so it depends on the shape too.
So theoretically,
Still
this is
recording for now.
just a sound that could like crush a person,
Yeah.
kill, like make them explode.
Machine.
I gotta keep this video up there so I can watch it. Make sure it doesn't shut down. All right. So if you don't have a slinky, that's okay. We all have slinkies here, but if you don't have a slinky, that's okay. You can use a rope or whatever, and you can do this first part with the rope. And this is the main part of it, so it's fine. So what you're gonna do, you can either have a partner hold one end of it, or hook it up to something like I did, or put something heavy on it. And yeah, we can see this. Yeah, no problem. Comes right here. Yeah, they can see this. And you make a wave. And we're gonna time how long that wave takes to go down and come back. We also, I want you all to pay attention to what the wave does and what it kind of looks like when it is down there. And then you should hold it in that space. But I'm going to put it up here. So once you see what the wave looks like, you position it still on the floor down there. I'm just putting it up here so y'all can see. You position it in whatever shape it was in. Right way. There we go. Okay. Hold on. Hold on. I can do this. I can probably make... No! There. Okay. Maybe. Maybe. Ding! So, okay, I made a wave. So, can they see that? They can see that. So your wave is probably not going to be as zigzag as this wave. It'll probably be nice and curvy like waves do. But you can measure the wavelength from here where it's connected to. They can't see that, can they? From there to this top part, from crest to crest, or you can do from trough to trough, which would be from this bottom part to where my other hand is down here. It's just wherever it starts repeating its pattern, right? That's the wavelength. You also need to count the waves, and there's not a spot on our table to write down how many waves there are, but you do need to know how many waves there are because you're going to need to know how many waves per second and how many seconds per wave. If you don't know how many waves there are, then that'll be messed up for you. So yeah, you can measure the wavelength like that. The amplitude is another thing to measure. Remember, the amplitude isn't from bottom to top up here. It's from the middle to the top. Oh, excuse me. So like the amplitude is, if you stop shaking the wave, it'll end up right in the middle there. It won't end up down here at the bottom, it ends up in the middle. So that's why you're measuring from this point up to where it was at its highest point. So if this wave relaxed, it would be it would end up here. So you measure from here to the top or from here to the bottom. Amplitude can work either way. I'm going to take this off before I break my slinky. So yeah, you get the wavelength, the amplitude. You'll also measure the whole length that the wave travels, which I'm saying is length between the ends of the spring or the rope or whatever you're using at home. So you'll measure from one end the straight line distance to the other end. Don't measure the whole curvy distance, just the straight line from here to there. That'll be how far the wave traveled. And when you time it, when you shake it, and you time how long it takes to go from boom, boom, to there, to the other end, there's your time. And then the first thing you can do with that, and you don't have to do this in any particular order, but once you get the meters it traveled and the time it took in seconds to go that far, you can get meters per second. Meters divided by seconds makes meters per second. Okay, that thing's still going. Good. Frequency is waves per second. That's where you need to know how many waves there are. And after you measure the wavelength, if you're not really sure how many of those waves fit, or if there's only really one wave and it just moves across the way, what you can do to figure out how many waves there are is you can say, okay, my wavelength is this much, but I have this much length between here. So if I have, say your wavelength is 1 meter, but your whole rope or spring or whatever was 2 meters, that would mean you would have 2 waves fit in there. So you can basically say this length divided by the wavelength gives you the number of waves. And then you can do that number of waves per second, so that number of waves divided by the time to get frequency, or seconds per wave is period. Remember, seconds per wave is, if there's, so let's say it takes 1 second for your thing to go past, but 2 waves fit in there, each of those 2 waves would get half a second. Because you had 1 second divided by 2 waves, each wave get half a second. So that's what period is. It's how long each wave takes. Since it's seconds per wave, you do your time divided by the number of waves there. And it would probably do you good to just try to make 1 wave fit in that distance, and then it makes it simple where you don't have to go figure out exactly how many waves fit. With the time, it's going to make it more simple if you don't stretch it out a lot, because if you stretch it out a lot, the waves go really fast. If you don't stretch it out as much, the waves go a little slower and it'll be easier to time. So yeah, that's all this top table. This bottom table is the one that I made optional for people at home. We have a slinky, so we can do it, but I'm not sure everybody's going to have a slinky or a spring or something else that you can do one of these with. So what I'm talking about is, I can do this right here, hold on. Okay, if you stretch out your slinky here, or whatever, you can squeeze up part of it, and then let it go. And so what we were making before, where the wave went up and down, but still traveled side to side, that's a transverse wave. This is a longitudinal wave, because when I compress it, the take 2. The compressed part moves down the length of it, and then it comes back. And we would time that and measure the length of how far it traveled and get the speed. And that's the only calculation to do with longitudinal waves. So measure how far it went from there to there, time how long it took, and meters divided by seconds makes meters per second. But and again, it'll be easier to time if you make it looser. But this is a longitudinal wave, because the vibrations in it move side to side, and then the wave also moves side to side. They're both going along the length of it, longitudinal. As you can see, slinkies can be very fragile, so please don't play around with them. Keep them on the floor. Don't lift them up and shake them around like this. That's not what we're doing. Y'all are taking two people and holding on to it and shaking it side to side on the floor. These are also a real pain to try to untangle, so please be careful. Any questions about what we're doing? All right. Please go try it out, the Waaaaave.
That's my video.